Okay, so 1.3, we're going to be talking more about functions and graphs, and we're going to start off with understanding how to describe intervals for increasing, decreasing, and constant, okay? So I took a couple of pictures from the book to put them in the lesson so that we could see a little bit better here. You don't necessarily have to copy down the picture, but we want to be able to copy down the ideas for increasing, decreasing, and constant. So I'm just going to ask you right off the bat here, what is this graph comparing? What versus what? Hours to what? To temperature. Okay, so we're comparing hours to temperature. So, and notice that the graph tells us that it's hours after 8 a.m. Okay, so if there's a 1 there, what time would that really be? 9. So 2 is 10, and so on and so forth. Okay, all right. So we want to talk about, where do you think, on what intervals? So when I say intervals, in this case, I'm referring to the hours. So on between which 2 hours would you say the temperature decreased? Amelia, what do you think?
Between, like, the start of the first hour.
Between, so if you had to give me a time frame, what would the time frame be for when you think the temperatures were decreasing?
Like, 0 to 3.
0 to 3. So how would we relate that into the problem here? Yeah.
8 to 11.
From 8 until 11. Does that make sense? So from 8 to 11, the temperature's decreased. Okay. What about increasing? Yeah, what do you think?
11 to 1.
From 11 to 1, the temperature's increased. Was the temperature ever really constant on our hours here that we've been given? No. So we kind of, when we just talk about these things, we have an understanding of what it means to be decreasing and increasing. The problem that I have found where students get confused is they don't know where to look on the graph. So I'm going to show you exactly where to look. So here's how I approach this, okay? I take like a highlighter, and you don't have to have a highlighter, but I take a highlighter and I go, okay, this right here is the portion of the graph that's decreasing. You guys agree with that? It's going down from left to right. So then what we do is, to describe where the graph is decreasing, is we look down on our x-axis, and that's our location of where we describe where the graph is decreasing, okay? So we could say this, the graph is now decreasing. So we're going to write this in a couple of different ways. It's decreasing from 0 less than x less than 3. That's one way that we could describe that. Now, this is called inequality notation. Inequality notation. Why do we call it inequality notation? Because there's inequalities in it, right? Really, it's really that straightforward, right? There's inequalities in it. Okay, what do you notice about the inequalities, though? What do they not have?
Equal.
Less than or equal to. The reason we don't put less than or equal to is because at that moment in time, it's never really equal to 101 degrees or 3. So 0 and 3 are not actually part of the interval. They're just the end caps of the interval. So we're saying between the hours of 0 and 3, and hours, of course, is after 8 a.m., we're saying the graph is decreasing. That's inequality notation. Another way that we could write this is using interval notation. And that would be without the inequality. So we could say from 0 to 3 with parentheses. Now, this is called interval notation. I-N-T-R-V-O. Okay, interval notation. And that's what most books use. I want you to be able to describe it in both ways. Now, that's not the point 0, 3. Don't get confused. Interval notation is either going to use a parenthesis if the point is not included, and it will use a bracket if the point is included. And we still read it from left to right. So we say it's decreasing from 0 to 3. So as an example, this would be incorrect to write it like this. Why would that be incorrect? Because 3 to 0, we don't read it backwards. We read it the same way that it's on the number line. Does that make sense? Okay, good. So that's one part there. Let's talk about where the graph could be increasing. Okay? Where's the graph increasing? Well, I do the same thing. I look at my graph and I say, okay, this is the highlighted portion for where the graph is increasing. So how do I describe it? I look down on my x-axis and I say between which 2 x values? 3 and 5. So in inequality notation, it would be 0 is less than, oh, not 0, excuse me. 3 is less than x is less than 5. And how would I write it in interval notation? Yep, parenthesis 3, comma 5. Very good. Absolutely perfect. Absolutely perfect.
It's still less than even so increasing.
Yes, the inequality, this part is less than. You're saying that your values are stuck between 3 and 5. So 3 is the smallest, 5 is the biggest, your values are in the middle. It's got nothing to do with the word increasing. Marin, what is that part? What does f of 5 equal 100? What is that trying to convey to you just in terms of what the graph is saying? Michael, what do you think, buddy?
When x is equal to 5, y is equal to 100.
So 5 hours past 8 a.m., the temperature will be 100 degrees. So I want you to be able to relate these things into everyday English words. Does that make sense? Okay. This is the same picture, but it's only talking about the decreasing part. Okay, it's only talking about the decreasing part. So let's write our interval. Where is this graph decreasing? How about we say it? From where? 0 less than x less than what? Less than 3. Very good. Okay, it's decreasing there. Now, let's also take a moment and let's talk about the domain for this particular graph. So the domain is all the x values, right? So what would the domain be in this particular case? Well, yeah, the domain would be all. I'm going to show you a way to write it. That's called set notation. And the set notation would be this. Who knows what this symbol means right here? All real numbers. So the domain will be all real numbers x such that, the little bar means such that, 0 is less than x is less than 3. So what we were saying there for the domain is we're talking about the x values. So again, what I like to do is I like to highlight my graph, okay? Highlight my graph, and then I look down on the x-axis for the start and the finish. That's my domain from 0 to 3. All right?
So it's in brackets y.
What's that?
So it's
Oh, sorry, these ones, we actually include these ones. I made a mistake here. These ones we do include in the domain. Why do we include those in the domain? Because we can actually plug them into the function, right? We can actually say, well, at the 8 a.m. hour, the temperature is 101, and at the 3 hours past 8, the temperature is exactly 98.6. So in our domain, we would definitely include the equals to 0 and 3. Millie, yeah, back to you.
always going to be all real numbers x.
All real numbers x, yes, for the
And
domain.
then you're always going to put the decreasing there or the increasing.
I put whatever the domain happens to be.
Okay.
It could be different. In this particular case, it just happens to be the decreasing. Michael.
Since it's all real numbers,
Uh-huh.
that includes like the decimals, so it could be like 1, where is it at 1.2?
Correct. Absolutely. Okay. Let's also talk about, for a moment, let's talk about the range. Okay, let's talk about the range and how we describe the range. The range is also a set of numbers, so we're going to use set notation. But instead of looking, I'm still going to highlight my graph, but instead of looking at the x-axis, what am I going to look at? I'm going to look at the y-axis. So I'm going to focus my attention back to the y-axis, and that's my range. So I'm going to say all real numbers. Do I say x here or do I say y here?
Y.
I say y because I'm talking about the range. All real numbers y such that, what are the two values that this graph falls between on my range? 101 and 98.6. We get that information from the graph, right? It says it right there. So we're going to say, okay, 98.6 is less than or equal to y, which is less than or equal to 101. So I have my domain written in set notation, and I have my range written in set notation. Let's take a look at this graph, all right? Let's talk about where this graph would be decreasing. Let's talk about where this graph would be increasing. Let's talk about the domain for this graph, and let's talk about the range for this graph. Okay? So first of all, let's start with the decreasing interval. So where would this graph be decreasing? 0 to 3. So I'm going to choose to write this one in interval notation. So from 0 to 3, that's where it's decreasing. Where would it be increasing? From 3 to 5. So I'm going to write this one in inequality notation. 3 less than x less than 5. Where is this, or what would be the domain of this particular function? From 0 to 7, exactly. It would be all real numbers x such that 0 less than or equal to x less than or equal to 7. Very good. What about the range of this function?
98.6 to 101.
Very good. So all real numbers y such that 98.6 less than or equal to y. Let me move over. Less than or equal to 101. Now, the only other thing we haven't talked about is constant. Okay, so where, on what intervals would this be constant? Well, this right here is the constant part. So where is the interval? Between where and where? So between 5 and 7, right? It's constant. So we would say between 5 less than x less than 7. I would like you to graph this function in your calculator, alright? And graph it on a standard window, and I want you to write down where the graph is increasing, where it's decreasing, and where you think it's constant. Check your work with someone sitting next to you. So 3x squared minus x cubed. Okay, this is a new function that we haven't yet seen. So let's take a look at what it's doing. So
So cool.
I know, it's a really nice little program here. So take a look at this, all right? How do we say where this thing is decreasing from? I mean, if I were to zoom out, right? If I were to zoom out on this thing, I mean, look how tall this thing gets, right? So no matter where I am on the x-axis, I can always find a point. Look, I'm at the negative 500 all the way up to 600. I could find this point if I really, really wanted to, but it would take me a very long time to get to the top, okay? So we could do it, but I'm going to just zoom back into something a little bit more interesting for us and just talk about maybe perhaps this window right here or so. That looks pretty good. So I'm going to take this picture. I'm going to bring it over to our notes so that we can talk about it, okay? So here's my notes. My notes have disappeared. It's amazing. Here they are. And let's talk about this picture. So here we go. I asked you to figure out the intervals where this thing is increasing, decreasing, and constant. So it looks like it's decreasing all the way until it gets to what x value? 0. So the first interval where this is decreasing is known as negative infinity up to 0. And I'm going to write that in interval notation. That's the first decreasing part. No, there's two infinities, right? This one's negative infinity, and this one is to positive infinity. Okay?
Why is this negative infinity?
Why is it negative infinity? Because give me the smallest number you can think of. Okay, negative infinity is all the way to the left, right? If you said, look, these numbers are negative, right? Negative 2, negative 3, negative 4. So the smallest one we can get is negative infinity. That's way out there.
Because it's on the left side.
It's on the left-hand side. And notice that this is still written from negative infinity up to 0, right? We still read it like a book. It would be incorrect to write it like this, 0, comma, negative infinity. Why would that be wrong? Emily, why would that be wrong? Yeah, because 0 is not to the left of negative infinity. Negative infinity is to the left of 0. So you read it, so the order does matter in which way we write those things. Now there's another place where this is decreasing as well. So if I was to highlight it on the graph, it would be from here to here. So how do I describe that?
4 to infinity.
From 2 to positive infinity, right? Remember, we're only looking at the x values, okay? Only looking at the x values. So this would be where my graph is decreasing. Okay? Jack, do you have a question?
Wait, so 2.
This graph is also increasing. I'm going to highlight the portion of the graph where I believe that the graph is increasing. Do you guys agree with that portion?
Yes.
Okay, now I look down to the x-axis to describe that portion. So how would you describe that interval where the graph is increasing?
0 to
There you go. From 0 to 2. That's where it's increasing. From 0 right there to 2 right there. So that's my interval where it's increasing. Yeah, Marin. All right, look. This is a graph. This is called a piecewise defined function. We're going to get into this a little bit later. But look, this is what's going on. I have two parts of this graph. There is this line that is shooting off to the left. The arrow indicates that it goes off to infinity in that direction. And notice that the point is also included on that line right there. Now, I have another segment of this graph where the point is not included, so I'm using an open circle, and this graph is going up, and the arrow indicates that it keeps going like that forever and ever. So, same exact task. I'm going to ask you, where is this thing decreasing? Where is this thing increasing? Where is this thing constant? Okay? That's what I'm going to ask you for that one. So, See if you can figure it out or just talk about it with the person right next to you. Okay, who would like to describe where this graph is decreasing? Decreasing. It's not. This graph is never decreasing. It's never decreasing. So, how do you tell if it's decreasing? You go from left to right. Does the graph go down? It doesn't. It's not decreasing. Okay? All right, where is this graph increasing? Marin, go for it. I know you got it. Okay. There you go. That's one way you could do it, or the other way you could do it is you would do open parenthesis 0, comma, infinity. That's where it's increasing from 0 to infinity. We don't include the 0 because that dot's not colored in, and we never put a bracket around infinity because that would include that we could actually encapsulate all of it, and we can't do that. Okay? All right, here we go. Constant. Where is this thing constant?
0, negative.
No.
Negative infinity to 0.
Ah, very good. So, parenthesis, negative infinity, comma, 0. Look at this bracket. Wait, why is there a bracket? Why is there a bracket? It's a closed dot. It's actually a part of that. No, this one actually, the way that this is defined, okay? When you're at 0, when x is 0, what's the output? The output is up there. It's on part of that constant line. It's not part of the one below. That's the difference.
So why is it bracket?
All right, the next topic from 1.3 is called even and odd functions and the symmetry that functions have. Okay, so I'm going to teach you the definitions right here. So let's talk about even functions first, okay? It's an if-then statement, okay? And here is the if-then statement. If, and then. So here's how it goes, okay? If f of x, or excuse me, rather, f of negative x is the same exact thing as f of x, then your function is even. That's the definition of an even function. I am going to show you an example of what I mean by f of negative x is the same thing as f of x. So that means that if you took the negative and plugged it in, you'd get the same thing as the positive and plugging it in. That's the definition of an even function, okay? Now, if your function is even, okay, then you have symmetry with the y-axis. You have symmetry with the y-axis, okay? If you have an even function. Now, what about an odd function? Well, here's an odd function. It's another if-then statement. It says if and then. Okay? So for us, if f of negative x is the equivalent of the opposite of f of x, that's what that means. If f of negative x is equivalent to the opposite of the function, then we define our original function as being odd. As being odd. So that's our definition. And if you have an odd function, then, I'll shrink this down a little bit, then you have symmetry with the origin. I know. Okay, I'm going to explain what symmetry with the origin means. It's kind of a tricky thing. Not many people understand fully what symmetry with the origin means. So here's our definitions for even and odd functions. Okay, it has something to do with f of negative x and comparing it to the functions. Okay, that's how we test for it. And then we also now know what it means if a function is even or odd in terms of symmetry. Okay, here's a typical question you're going to have to do tonight for the homework and on the test and on the quiz. I'm going to give you a function. That function is defined as x to the fourth minus 2x squared. And I'm going to ask you, is this function even, odd, or neither? Not every function is even. Not every function is odd. Right? Sometimes functions are just neither of the two. Okay? So let's talk about how we go about testing whether or not this is even, odd, or neither. So what we do is we write down, okay, well, let's figure out what f of negative x has to be. I already know what f of x is. It's right there. It's defined for me. So now I want to figure out what would f of negative x be. Well, what does that mean? That literally means take every x that I have and make it negative, right? So plug in a negative x. So it would be negative x to the fourth minus 2 times a negative x all squared. Then I have to use a little bit of algebra and think, okay, if I take a negative number and I raise it to the power of 4, what will that number be? It will be positive, won't it? So that's the exact same thing as taking x to the 4th. No matter what you do, you're going to get that in return. Okay, minus 2. Now, take that exact same argument. If I take a negative number and I square it, what number am I guaranteed to get? Also a positive, so that's the same thing as taking the regular number and squaring it. Now, ladies and gentlemen, take a look at what you've got. You have this information which matches exactly to that information. You guys agree with that statement? They're identical. So that tells you that this thing is the same as that thing, right? Because their outputs are the same. Now let's go back to the definition. If f of negative x is the same thing as f of x, what must this function be? Even. It must be even. Okay, this is an even function. Okay? Now, I'll get to your question in just a second. I want to show you something. If it's an even function, guys, if this is an even function, what would I expect the symmetry of this function to be? It should be symmetric with the y-axis. So I'll go ahead and give you the fast version of this one. It was y equals x to the 4th, right? Minus 2x squared, right? Okay. So I'll go ahead and graph this one, and you guys tell me, does it look like it is even with or symmetric with the y-axis? Yeah. If I plug in the line x equals 0, there we go. Does it look like a mirror on the left and on the right? That's what that means to be symmetric about the y-axis. You guys get a pretty good picture of that? Okay, let's take a look at what something else would look like. Okay, same question. I'm going to give you a function, x cubed minus 6x. I want to know if this function is even, odd, or neither, and then talk about its symmetry. Even, odd, or neither, and talk about its symmetry. Most likely, but let's check it out and see. All right? So I'm going to do the same procedure. I already know what f of x is. I'm interested in what f of negative x would be. So that would be, take my negative x, cube it, subtract 6, and multiply it by negative x. Okay, let's use some algebra here. If I take a negative number and I raise it to a power of 3, that number will be what? It will be negative. So that's just negative x cubed. Negative 6 times a positive, or negative 6 times a negative x is going to be a positive 6. So that's a positive 6x. Now compare. Is this thing the same as that thing, yes or no? No, they're not the same. So that means that f of x is not the same as f of negative x. So that tells me it's not even.
Do you always plug in just any negative number?
I plug in f of negative x to check.
And if it's f of negative x, you plug in the
No,
positive.
I always check f of negative x and the negative of f of x. So let's talk about what is the negative of f of x. That literally means the opposite of f of x. X cubed minus 6x. That's what that means. The minus sign is on the outside, right? So I want the opposite. Go ahead and simplify that. That's negative x to the 3rd plus 6x. Well, shoot. Look at that. What is that thing the same thing as? That is the exact same thing as that. So that tells you that negative f of x is the same thing as f of negative x, which implies that we have an odd function.
Couldn't you just get that from the first equation and not the second half?
All right, let's talk about what it means to be symmetric with the origin. All right, here's what it means. What do you, looking at this graph, where do you think there is definitely some kind of symmetry here, right? But it's not the y-axis, it's not the x-axis, it's not a diagonal. What is it?
It's opposite symmetry.
So it's opposite symmetry. What does that mean?
It's like, I don't know.
It's like a mirror, but it mirrors along it mirrors like this way instead of the.
Okay, here's the best way. Here's the
along
best.
the y-axis, it's a mirror.
Okay, here's the best way that I could describe what symmetry with the origin means. Okay, pick any point that you want on the graph. Pick any point.
12 and 6.
I can't really see 12, 6.
Whatever.
So give me one that you can actually see.
2 and 40.
2 comma 4. That's not on there either.
2 negative 4.
2 negative 4. 2 negative 4. This one. Okay, there you go. So we're gonna call that point 2 comma negative 4. That's a point that we can actually see on the graph, right? And here's what it means. If you draw a line straight back to the origin and then go the exact distance in the opposite direction, that point is also guaranteed to be on the line.
-2 positive 4.
Negative 2 positive 4.
So you just flip the signs.
Mm-hmm. So check it out. If I said this point is on the graph, if I draw a line to the origin and then go the exact distance in the opposite direction, that point is also guaranteed to be on the graph. That's what it means to be symmetric with the origin. Pick any point that you want. Here's a nice purple point up here. Draw a line to the origin, go through it, go the opposite direction in the same distance, and that point is also guaranteed to be on the graph as well. That's what it means to be symmetric with the origin. Kind of a trippy thing. Okay, the final idea from this section is what's called a piecewise defined function. And all that really is just a function that's defined in different pieces. Okay? So here's one for example.
On the other side as well.
Oh, what's that?
Do you put the curly Q bracket on the other side as well?
Actually, not for these ones. You don't put it on there. It's customary not to. I don't really know why. Customary. So here's the deal, right? So you give me a value of x, and all I do is assign it to the proper function. Okay? I'm going to highlight this one as the yellow function, just for now, and then I'm going to highlight this one as the green function for now. Okay? So I'm going to ask you guys to give me an x value. Give me an integer, any integer x value. Just shout one out. 3. Okay, if you give me 3, I would plug it into the green function. Why? Because Barry is okay. Give me another one. 2. I'd also plug that one to the green function.
Why?
-2.
Wait, why?
84.
84, also in the green function.
-2.
Also in the green function. -5, yellow function.
Oh, because it's negative.
Yeah, what defines, how do I know what to do with what number?
Well, there's positive or negative.
It's all determined by this value over here, okay? So they're going to give you a piecewise defined function, and they're going to say, okay, evaluate what would f of -3 be. How do you get this problem wrong?
If you plug it into
You plug it into the green function. So f of -3, because -3 is less than 0, I use the yellow function. So f of -3 would be a value of 6 times -3 minus 1, which is -18 minus 1, which is -19.
So if you're like unsure, you could do it in both, and then it just has to be true on the other side.
You have to look here. This is where you look. Yeah, this is where you look.
If you didn't know, I'm saying I could plug any value into both, and then it's whichever one of those statements becomes true.
Well, it's not
So
whether
it's
it's
gonna be-
it's not whether it's true or false, because I could plug 0 into the green one.
But then it won't be a true statement of X's,
Yeah,
is what I'm saying.
How is it a true statement?
It's not. There's no true statement here. There's no true statement. That's not what we're trying to define. Okay. I look here. This tells me which. It's like a door, right? Which door do I go in? Right? Here. What would this one be? How do you evaluate f of 0? Which one do you put it in? You put it in the green one. Why does it go in the green one? Because it's equal to 0. Exactly. So this one would be just a value of 3. What about if I ask you what's f of 5? Which one do you put it in? You put it in the green one, because 5's bigger than 0, right? So there's no truth, Michael. It's just which one do I put it into? Do I put it in the yellow or put it in the green, right? So put it into this one. It'd be 35 and 3, so 38, right? Okay, so you're going to have to do that tonight.